Hello everyone, welcome back. In our today's video, we will be continuing with P block elements, that is group 15 elements. But today we'll be discussing about nitrogen and its compound. So let us start with our first topic of the video, that is dinitrogen. So first we'll try to see how do we prepare dinitrogen in lab. So in the laboratory, it is prepared by heating an equimolar mixture or equivalent mixture of ammonium chloride and sodium nitrite. You can see in the equation that ammonium nitrate aqueous solution, ammonium chloride aqueous solution is taken, and sodium nitrite aqueous solution is taken and heated together. Remember that when you take ammonium chloride and sodium nitrite, it first gives you ammonium nitrite, which when heated decompose to give you nitrogen and water. And the byproduct of the reaction of ammonium chloride and sodium nitrite is nothing but sodium chloride, which you can see over here. The second way of preparing nitrogen in lab is by thermal decomposition of ammonium dichromate. This is ammonium dichromate, NH42Cr2O7. Thermal decomposition, so we have to heat it. When we decompose it, it gives you nitrogen, water, and chromic oxide. We can prepare dinitrogen by thermal decomposition of sodium or barium azide also. When we say azide ion, basically it is N3 minus, 3 nitrogen having a common charge of -1. So Na plus and N3 minus. So NaN3, that is sodium azide. We can take barium azide also, which is very common. So if we take sodium azide and heat it, it gives you sodium and nitrogen. So these are the various ways how we prepare nitrogen gas. Then what are the properties of nitrogen gas? Nitrogen gas is a colorless, odorless, and tasteless gas. It is non-toxic. It has very low solubility in water. It is neutral towards litmus. It is neither acidic nor basic. It is chemically unreactive at room temperature. And remember that the chemical inertness of this particular compound, this particular molecule, is because of the triple bond which the two nitrogen has. The decomposition temperature or the decomposition energy or the bond dissociation energy of this particular molecule is very, very high, as a result of which it remains inert at room temperature. So basically, two nitrogen molecule in N2 has a triple bond, okay, which we called as p-pi multiple bonds in nitrogen. So you can see in the last line, the nitrogen bond in molecule is a triple bond and hence high bond dissociation energy. As a result, N2 is inert at room temperature. And remember that it is neither combustible nor it support combustion. Okay, so these are some of the properties of dinitrogen gas. Coming for the next compound of nitrogen, that is ammonia. Very important, okay, very important molecule for the preparations of fertilizers, okay, especially. So ammonia, how do we prepare it? So ammonia is prepared industrially by Haber's process. Now, what is Haber's process? You can see in your screen, in Haber's process, you take nitrogen and hydrogen in the ratio of 1:3 and react it in a specified condition of 700 Kelvin, 200 atmosphere, and in the presence of catalyst, which is a mixture of iron oxide, potassium oxide, and aluminum oxide with molybdenum as a promoter, which gives you ammonia gas. And remember that the heat of formation of this particular reaction is -46.1 kilojoule per mole, which shows us that it is an exothermic reaction. Now, the question is, why do we require such condition? And what is the favorable condition for the maximum yield of ammonia? So, if you see this particular reaction, since this reaction is nothing but an exothermic reaction, which we can see from the value of the heat of formation, that is -46.1 kilojoule, this tells us that this particular reaction is exothermic. Now, according to Le-Chatelier's principle, any exothermic reaction is always favorable at low temperature. So remember that the formation of ammonia, if you want more ammonia, if you want maximum yield for ammonia, what you require is the reaction to be done at low temperature. But remember that when you carry out the reaction at low temperature, according to the chemical kinetics, as the temperature decreases, the rate of reaction also decreases. That's why this reaction is not carried out at low temperature, but at an optimum temperature, which is nothing but 700 Kelvin. Okay. We cannot carry out the reaction at a higher temperature, because if we carry out the reaction at a much higher temperature, although the rate of reaction will be faster, but remember that the rate at which ammonia will decompose back to nitrogen and hydrogen will also increase. As a result, we prefer it to carry out at an optimum temperature of nearly to 700 Kelvin. This particular reaction is carried out at a very high pressure, nearly at 200 atmosphere. Now, why it is so? According to Le-Chatelier's principle, any reaction which is accompanied by decrease in the number of moles, which you can see that nitrogen is reacting with hydrogen, which is 1 and 3. So total number of moles is 4, and 4 moles is giving you 2 moles, which tells us that the number of moles in this particular reaction decrease as it proceeds forward. As a result of which, since the forward reaction proceeds with decrease in the number of moles, hence increase of pressure, according to Le-Chatelier's principle, will favor the forward reaction and maximum yield of ammonia. That's why the reaction is always carried out at high pressure. Coming for the third condition, that is the use of catalyst. Why do we use catalysts? As already mentioned, that since the temperature is not very high temperature which we are taking, because if the reaction is exothermic, we cannot carry out the reaction at a high temperature, which will favor the backward reaction, that is the decomposition of ammonia. That's why this reaction is favored at a low temperature or at an optimum temperature of nearly to 700 Kelvin. Since at low temperature, the rate of reaction is slow, that's why catalyst is used to enhance the rate of reaction. So the catalyst which we use is iron oxide, potassium oxide, and aluminum oxide. But remember that sometimes in some of the cases, we use molybdenum as a promoter for this particular reaction. Now, what is a promoter? A promoter is a substance which itself will not act as a catalyst, but it increases the efficiency of a catalyst. So molybdenum here act as a promoter. So these are the conditions in which you get maximum yield of ammonia by Haber's process. Now, coming for the properties of ammonia. Ammonia is a colorless gas but has a characteristic pungent smell. Okay, it is highly soluble in water, and remember that it's basic in nature. And its aqueous solution will be weakly basic. Now, why it will be weakly basic? Because due to the formation of hydroxide ion. You can see on the screen that whenever ammonia gas reacts actually with water, when you dissolve it in water, it gives you ammonium hydroxide. And remember that ammonium hydroxide, being a weak base, will not dissociate to a large extent. As a result, it gives you less concentration of hydroxide ion in this solution, which makes the solution weakly basic, not strongly basic. And why it is the ammonia itself is basic in nature, it acts as a base. Why? Because of the presence of lone pair on nitrogen. Because of the presence of the lone pair on nitrogen, it acts as a Lewis base, okay, which is available for donation. Because of the availability of this particular lone pair on nitrogen, since it is acting as a Lewis base, remember that because of this, it acts as a very good complexing agent. Or in simple words, we can call it ligand. Ammonia combines with various metal ions, various transition metal ions to give you coordination complexes. One such example is given like when you take copper sulfate, okay, or Cu2 plus ion. So which is actually whenever you take copper sulfate, obviously it makes the solution blue. Okay, it's blue color crystal. You dissolve in water, it will make the solution blue. You add few drops, or you can actually take ammonia gas, or you can take ammonium hydroxide, react with it. The moment you do so, it gives you a deep blue colored solution. That deep blue colored solution is nothing but because of the result of the formation of the coordination complex, okay, which is nothing but tetraamine copper 2 complex, okay, and this particular complex results into the deep blue coloration of that particular solution, which is nothing but a coordination complex. So remember that because of the presence of the lone pair on nitrogen in ammonia, it acts as a very good complexing agent or ligand. Okay. Now coming for the third important compound of nitrogen, that is nitric acid, a very common acid. So let us first see the laboratory preparation of nitric acid. In the laboratory, nitric acid is prepared by heating sodium nitrate and sulfuric acid. So you take sodium nitrate and you take sulfuric acid. When you heat it, it gives you, it's basically a displacement reaction where the sodium gets displaced by hydrogen, giving you HNO3, and the side product will be sodium sulfate. So that is how actually we prepare nitric acid in lab. Now, nitric acid is prepared in industry or for commercial preparation is done by a process known as Oswald process. The basic principle of this particular process is the oxidation of ammonia by atmospheric oxygen in the presence of platinum or rhodium as a catalyst at 500 Kelvin and 9 bar pressure. Whenever you do so, whenever you oxidize ammonia, what it gives you is nitric acid, NO, and water. This nitric acid reacts readily with oxygen to give you nitrogen dioxide, which can be easily traced because nitric oxide is a colorless gas, but the moment it reacts with oxygen, it gives you a brown gas, which is nothing but nitrogen dioxide. Nitrogen dioxide being very easily actually soluble in water. Okay, if you take nitrogen dioxide and dissolve in water, what it gives you is nitric acid, and the side product is nitric oxide. This nitric oxide is again used in the second step to give you nitrogen dioxide again. So nothing goes in waste, and your main product, that is nitric acid, is also formed. So that is what actually we call as Oswald process. So remember that this process is basically based on the oxidation of ammonia by atmospheric oxygen. Coming for the properties of nitric acid, one of the very important properties of nitric acid is it is a very strong oxidizing agent. And why it is so? Because it easily decomposes to give you nascent oxygen. Okay, whenever you heat nitric acid, okay, it decomposes on boiling or in presence of sunlight also to give you nascent oxygen. That nascent oxygen reacts with metals and non-metals to give you different oxidation reaction. Now remember that dilute nitric acid has no action on non-metals. Okay, so dilute nitric acid cannot oxidize non-metals, but concentrated nitric acid oxidizes many non-metals. And remember that all these non-metals get oxidized to their oxo acids. Some of the examples is shown in the figure or in the screen. You can see over there, like sulfur, when it reacts with nitric acid, it gives you sulfuric acid, that is the oxo acid of sulfur, the side product of oxidation. Whenever nitric acid gets oxidized, it gives you nitrogen dioxide and water. Whenever phosphorus is oxidized with nitric acid, it will give you phosphoric acid, nitrogen dioxide, and water, which is the side product. Iodine get oxidized to iodic acid, and carbon get oxidized to carbonic acid. Basically, it's carbon dioxide in water. So this are the various examples for the oxidation of non-metals by concentrated nitric acid. So remember that the nitric acid which we are taking over here is concentrated nitric acid. If it is dilute nitric acid, it has no action on non-metals. Coming for the oxidation of metals, whenever nitric acid reacts with metal, remember that they always form metal nitrates, and the nitric acid itself is reduced to nitric oxide, nitrogen dioxide, nitrous oxide, N2O, or ammonia, depending upon the concentration, activity of the metal, and the temperature. So the reaction with metal depends on the temperature, the concentration, as well as what kind of metal, how much active the metal is. That will decide what the nitric acid will get reduced to. But the metal always get converted to metal nitrates. So let us try to see two very common examples of copper and zinc. If copper is reacted with nitric acid, if I take concentrated nitric acid, it gives us copper nitrate. That is what any metal will convert into copper. It's nitrate, so copper nitrate. But the side product which you get over here is nitrogen dioxide and water. The same thing when copper reacts with dilute nitric acid, it gives you copper nitrate, no doubt, but the side product, now since the concentration is changing, so it gives you nitric oxide. Same way when zinc reacts with dilute nitric acid, it gives you zinc nitrate, that is the metal nitrate. The side product which you get is nitrous oxide. Similarly, when zinc reacts with concentrated nitric acid, it gives you metal nitrate, zinc nitrate, no doubt, but it gives you nitrogen dioxide. So the nitric acid reduced to which form, that depends upon what kind of metal you are reacting with and what is the condition in which the nitric acid is reacting with metal. But remember that the metal will always be converting into its nitrate form. So these are some of the examples how nitric acid reacts with metal. Now, a very common qualitative analysis test which we do for nitrate ion, which is nothing but brown ring test. So remember that this particular test is a qualitative analysis for the detection of nitrate ion in a particular given sample. The pictorial representation is actually shown in the figure. Okay. So what you do in this brown ring test is we take an aqueous solution of the nitrate ion, the sample which is provided to us, which contains nitrate ion. To test it, first we take an aqueous solution, mix it with freshly prepared ferrous sulfate solution. So the solution of ferrous sulfate must be freshly prepared, and we take this particular mixture together, ferrous sulfate solution and aqueous solution of the sample, that is our nitrate ion. Once the sample actually is mixed with ferrous sulfate solution, then if you can see in the figure, the test tube is tilted, okay, and we add concentrated sulfuric acid, almost to 98% pure sulfuric acid, and it has to be added dropwise and along the side of the test tube. Be very careful. You are adding acid to water, which is very much exothermic. H2SO4 and water, whenever it mixes, it's a very exothermic mixture. So the acid has to be added very carefully, dropwise along the side of the test tube and very slowly. When doing so, what will happen is, since H2SO4, concentrated H2SO4, it's much denser than that of water, then this H2SO4 slowly goes without mixing and resides on the bottom of the test tube. So as you go on adding, since there is a difference of the density, what you will get is the concentrated H2SO4 goes below, and the water with the nitrate ion and ferrous sulfate solution will come on the top of the H2SO4 solution. This will be separated clearly since they have two different density, but in the interface, the ferrous sulfate, the acid, and the nitrate ion comes in contact, and in the surface, in the interface of this two liquid, the reaction takes place. The reaction is shown where nitrate reacts with ferrous sulfate, that is Fe2 plus, in presence of acid 4H plus, to give you nitric oxide, that is the ferrous converts into ferric, and water. This nitric oxide will react with the ferrous sulfate in presence of water to give you a coordination complex, which is nothing but penta-aqua nitrosonium iron 2 complex. Okay. And this particular complex which forms is actually brown in color. So that particular complex forms on the interface of the concentrated H2SO4 solution and the mixture of the nitrate ion and the ferrous sulfate solution on the top. So whatever reaction will happen on the interface, as a result of which this complex forms on the interface. And since the test tube is circular, as a result of which what you can observe is a ring. That is what we called as a brown ring. And the overall test is known as brown ring test. So that brown ring is nothing but penta aqua nitrosonium iron 2 complex, which is a coordination complex of iron. So that is how actually we test for nitrate ion. So if the brown ring appears, that means nitrate ion is present in the given mixture. If brown ring will not appear while doing this test, that means nitrate is absent. So that is how we do qualitative test for nitrate ion. So that is all about the nitrogen and its compounds. So thank you everyone. To subscribe for this channel for explanation on various topics in chemistry. Thank you.